Good morning, everybody. Um, so I can't see any of you. Remember, if you can, please turn off your cameras turn on your cameras so that I can see your reactions to what I'm doing. Thanks. All right. I realized that it actually hasn't. It's been a while since we met for lecture because last week we had a snow day, and then we had exams. So we didn't actually cover any new content since the week before that. So it's been a while. Some quick announcements about the exam. I've graded most of it. I've graded all of the sort of numerical questions, but not the essay questions yet because they take longer to grade because I got to read carefully. And there's still a few of your classmates who haven't taken the exam yet. So once that's done, I can like talk about specific questions and post your grades online. But most of you did pretty well, like amazingly well. So maybe I was thinking maybe exam was too easy. I don't know. No, you guys did great. You guys did great. Some of you made some like silly math mistakes, like algebra, or you like misinterpreted how to read the integrals or differentials that I posted. But apart from that, most of you did really well. But yeah, they're pretty much all graded, like I said, but I won't post anything until everybody's taken the whole exam. Apart from that, yeah, that's all the announcements I have. Any questions on that without giving away anything to those who haven't taken it yet? All right. Um, I also posted your third Jupyter notebook on ACE. You should have a link. It's the same process as the second and the first. Um, spent a long time programming this one, but hopefully this one you'll see some cool things about wave functions that I'm trying to explain in class, but they're difficult. For example, what does it mean when we use complex numbers for functions, and what happens when you actually see these waves moving? So hopefully that'll be cool. And so it's like less figuring out stuff and more just understanding how waves behave and how wave functions behave. But with that, let's jump right into it because it's been a while since we actually we've done anything. So, oops, I need more space. All right. So just a quick recap because it's been a while, right? In this chapter, we started talking about sort of we need to set up a theory of waves to describe matter because we learned that to describe all the phenomena that we see, we need to think of matter as both particles and waves. So we need a theory of waves to describe particles. And to do that, we've come up with a set of postulates, some sort of ground rules that we need to set up. The first of which was we need some function, we'll call the wave function, um, to describe these particles, right? And we went over rules of wave functions and how they must be continuous and all that good stuff. Now we don't know what the wave function really means, right? The wave function is not necessarily a function of how the particle moves. It's just we um, we don't have a good interpretation for what it is, but we learn from the Born interpretation that we can think of psi star psi, the integral of psi star psi, as the probability, right? So we don't know what the wave function is, but we know that if you sort of square the wave function and you integrate, that's the probability. But what we do know is all of the information about the particle is contained within that wave function. If you want to know anything about it, you actually perform operations. So any observable from that wave function has an associated operator. And so anything that we want to know about waves, we can just take that wave function and apply some operator to it, and we'll get that observable. And then the third sort of postulate was that the only observables that we could get are those that sort of set up an eigenvalue equation, right? So far we've only learned about these three postulates. And we've learned about normalization, right? We learned that if you integrate psi star psi, right, over all space, and all space just means sort of the where the particle is, then this should be equal to 1 if it's normalized. If it's not normalized, then it'll be some other number. And then we can get that normalization by doing this, right? All space. In general, we would want all of our wave functions to be normalized, but that's not going to always be true. So that's sort of where we left off. We started talking about the Schrodinger equation. And we mentioned that sort of what we want to learn here is to write the time independent, oops, independent Schrodinger equation, I'll just call it SC for now, for simple systems. And we should also be able to find the energy using the time independent Schrodinger equation. And then what we what we started talking about is we need some way to figure out what psi is. What is it? We talked about the fact that it contains all the information that we ever need to know. We talked about how we can use operators on them to get useful information out them. But what is psi? How do we find psi? Because while we talked about sort of what wave functions can be, right? Like you can draw any valid wave functions. Specifically, how do we find a wave function for a specific setup? And so what Schrodinger did is, well, he stated, let's start from classical mechanics, right? Where we know that the Hamiltonian, right, is equal to kinetic energy plus the potential energy, right? So, and this is the total energy, let's put it that way. And he was like, well, what if we apply this to the wave function, right? Because we know that total energy in a system should remain constant, even if the kinetic energy and potential energy change, right? Like the total energy of any system should be constant. So he's like, well, let's examine the Hamiltonian. This is classical mechanics, and let's apply this to our wave. And just for reference, remember the kinetic energy in Hamilton's equations was p squared over 2m, right? Where p was just the momentum, mass times velocity. Okay, so Schrodinger was like, let's use the Hamilton's equation, but in wave mechanics, and again, the wave mechanics was something that people have studied, right? This is not something necessarily new. People study waves and waveform long before quantum mechanics. In wave mechanics, right, this idea of a position operator becomes x multiplied by something, right? So this is our position operator. And the momentum operator is negative I h bar d dx. Okay. So we're not necessarily going to go into exactly why the position operator has this form and the momentum operator has this form. These come from wave mechanics. But we know that if we're working with waves, we don't need a kinetic energy value and a potential energy value. What we need are operators, not values, because we can get the values once we use the operators. So we need operators for kinetic energy. We need operators for potential energy. So let's find the kinetic energy operator. Kinetic energy operator. Right? So we know that kinetic energy is p squared over 2m. So the kinetic energy operator will be the operator for momentum squared over 2m, right? Basically, we just take the classical operator and we plug in the classical equation for it, and then we plug in the operator there. So what does that become? P is negative I h bar d dx, and it's squared, right, over 2m. Now, negative times negative, right, it's squared. Negative times negative is positive. I times I is negative 1, right? So negative I squared is actually negative 1. I could do that slower. So negative I times negative I is the same as negative 1 times I times negative 1 times I. So negative 1 and negative 1 is positive. I and I is negative 1. I only brought that up because a few of you made that mistake of like, how do you square negative i's on the exam? All right, so negative I squared is negative 1. H bar squared becomes H bar squared, right? And d dx squared becomes the second differential, right? That's what happens when you square a differential operator. It's kind of like d dx times d dx of something. You take the first differential, then you take the second differential, right? It becomes, you take one differential, then another, it becomes a second differential. So d dx squared becomes d squared dx squared, all over 2m. So if we simplify this out, the kinetic energy operator is negative, I forgot the negative sign there, negative h bar squared over 2m times d squared dx squared. All right, so that's the kinetic energy operator. What about the potential energy operator? So we have an operator for the potential energy. Operator, right? Well, remember when we were looking at Hamilton's equations of motion, the kinetic energy is always half mv squared, or in this case for quantum mechanics, this is always the kinetic energy operator. But the potential energy operator depends on the system, right? So it depends on what you're looking at, the potential energy is going to change. If you're looking at an atom versus you're looking at a ball rolling down the hill or a spring moving, your potential energy will change depending on the system. So it will depend on the system. So when you want to write this generally, we'll just put something like this. We know that potential energy depends on position, so we'll just write it as a function of x. X is position, right? Depends on position. So we'll just leave this like this. Once we go look at specific systems, then we'll write specific types of potential energy operators. But for now, we're just going to leave it general with a V as for potential energy with a little hat over it. Sometimes you'll see the kinetic energy also written as T with a hat over it. Either is fine. I use this one a lot in my papers if you read those. But there we go. We have the kinetic energy. We don't really have a potential energy, but we have a form for it. So if we put this all together, we know that the Hamiltonian is the kinetic energy plus the potential energy, right? So we just, in the operator forms, we just put little hats over them. If you want to write this out, the kinetic energy we said is negative h bar squared over 2m times d squared dx squared. And then the potential energy we can write as a function of position. In 3D, so this is in one dimensions, right? We only have x in 1D.
Could you scroll up a little bit?
Oh, sorry.
Thank you.
So if you're thinking in real world, we don't have one dimensions, right? We have 3 spatial dimensions. So in 3D, the kinetic energy operator will be the same negative h bar squared over 2m, right? But we have the second differential with respect to x, we have the second differential with respect to y, and we have the second differential with respect to z, right? Note that I'm writing partial derivatives here, not whole derivatives, right? This is partial. So it's not like a solid D, it's this little curly D. And the reason we're doing that is because we don't know what this is going to apply to, right? So just write partial derivatives. Honestly, there is no difference. Again, I'm not a mathematician. I'm sure a math professor is going to disagree with me. But in terms of applicability, there is no difference between these two. It's just sort of what type of functions they're applied to. So there we go. All right. So that's the kinetic energy operator in 3 dimensions. But because this whole thing is, cumbersome to write, we often simplify this as this. And this is what you saw on the equations and constants sheet. This nabla squared is taken to be the second derivatives in each of the 3 dimensions. But obviously, if you're only looking at 1 dimension, nabla will be just the d partial d dx or d squared dx squared. If you're looking at 2 dimensions, it'll only represent 2 dimensions and so on. And similarly, in 3 dimensions, right, the potential energy operator will depend on positions in x, y, and z, like that. So if we rewrite the whole Hamiltonian now, right? Remember we said the Hamiltonian is the kinetic energy plus the potential energy. In 3 dimensions, this becomes negative h bar squared over 2m nabla squared. This guy here is nabla, right? I don't think it's a Greek symbol. It's sort of just an upside down triangle. Yeah, I don't think this is a Greek symbol at all. All right, so that's the kinetic energy, and then the potential energy depends on x, y, and z. So that's the Hamiltonian. So what did we just do? We made an operator for the kinetic energy. We have an operator for the potential energy. We put them all together to get a total energy operator, right? So that is called the Hamiltonian, which is basically the total energy operator, right? It contains the kinetic energy and potential energy. Those are all the only kinds of energy that, well, we know of, right? So to put this all together, remember we say that if we want any observable, we need to set up an eigenvalue equation, right? So we have some operator, let's call it O hat. We apply it to the wave function and we'll get the observable times the same wave function. Well, we're going to do that with the Hamiltonian as well. If we apply the Hamiltonian to the wave function, we should get back some constant, and that constant will be the energy, right? Because this is the energy operator times the same wave function. And that there, ladies and gentlemen, is the time independent Schrodinger equation. So the wave functions here should be eigenfunctions, right? Eigenfunctions. And this is the, oops, let's use a different color. That's the eigenvalue, which is the total energy. So this is it, an equation with 5 symbols in it, right? a Hamiltonian operator, two wave function symbols, right? Symbols for the wave function, an equal sign, and E for the energy. So five symbols, if you write that out, it's probably less than an inch long on your page. Yet, and again, I could be biased. Yet I think this is the most important equation in all of science. Again, I'm a biased person. This is what I study. But this little thing contains all of the sort of information about how matter works at all scales, really, but in particular how things work at the smallest scales. And that is the entire sort of foundation of quantum mechanics. Now, we're going to talk about the like time dependent Schrodinger equation, which is technically the equation, the more sort of the equation that we should be working with. But since this one is easier to solve, we're going to work with this one mostly throughout this class, right? If we wanted to write this out, we just expand out the Hamiltonian, right? And instead of writing the Hamiltonian, we write negative h bar squared over 2m nabla squared plus the potential energy as an operator times the wave function is equal to energy times the wave function. If you wanted to write it out a little bit longer. But this is the shortened form because now we all know exactly what the Hamiltonian actually is. So let's look at, I'll keep that right there. So let's look at some simple examples. I said one of the objectives of this part was to learn how to write the Schrodinger equations for simple systems. So let's write the Schrodinger equation for a one-dimensional system on the x-axis, in case you're wondering which axis, with zero potential energy. And I'll do this one quickly. Well, the Hamiltonian, right, will have the kinetic energy plus the potential energy. But if the potential energy is zero, the Hamiltonian then just becomes the kinetic energy, right? And since it's only one dimensional in the x-axis, I can write it as that instead of nabla. So if I'm writing the Schrodinger equation, it becomes this, right? There's no potential energy, right? So I can get rid of the parentheses. There's the wave function. That's the energy, and that's the wave function again. Easy, right? Like we know the potential is zero, so we only write the kinetic energy. That's the Schrodinger equation for a one-dimensional particle moving in one dimensions with zero potential energy. All right, how about you try one? Earlier, I think we looked at classical mechanics with particles moving in gravitational field. So write the Schrodinger equation for a particle, and again, just use one dimension in the z-axis, right? In Earth's gravitational field with the potential energy as being negative mgz. So if you have any questions about any of these, please let me know. But the first step is to write the Hamiltonian, right? We know it's the kinetic energy, which is going to always be the same. And in this case, we're working on the z-axis only, so we'll write that plus the potential energy, right, which is minus mgz. So I guess we can get rid of that plus sign there. So that's a Hamiltonian. So the Schrodinger equation then just becomes negative h bar squared. That's too tiny. Negative h bar squared over 2m d squared z squared minus mgz psi is equal to the energy times psi. That's a Schrodinger equation for that particle. Well, there's more than just sort of being able to write the Schrodinger equation. We can actually solve for the eigenvalues, right? We've solved eigenvalue equations before. We can do it again now, just in using this operator. So let's say an electron is described by the wave function it's a one-dimensional wave function, so it's only a function of x. And I'm going to write it out, sine pi x over a, where a is a constant, right? The potential energy is, let's just set it to 0, make it simple. Verify that this wave function is an eigenfunction, and find the energy, which is basically the eigenvalue. So I want you to write this question down, and then I'm going to break you up into some small groups, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Maybe groups of 3 to 4, maybe. And I would like you to work on this. I'll give you some time. And then once you're done, you can exit the breakout rooms and come back here and we'll talk it over. But theoretically, you should have all the tools you need to solve for this problem. So, oh, somebody's been typing in chat. Sorry, I didn't see that. So earlier somebody asked, when I say simple system, do I strictly mean one dimension? No, I just mean systems where the potential energy remains easy to write, right? Or easy to solve. So systems where the potential energy is 0 or something simple like negative mgz, those are easy. When the potential energy gets crazier than that, it becomes less simple. But that's a good question. But also most one-dimensional systems are also sort of simple. All right, breakout rooms. So yep, spend some time in your breakout rooms. And the reason I'm sending you in breakout rooms is if somebody help each other along, essentially, through chat or speaking. And then once you're done and you think you have an answer, just exit the breakout room. So I'll be sending you there now. My screen just went crazy by jumping into various breakout rooms. All right, I'll end the breakout rooms. And now to fix my screen. I have no idea how to fix my screen. What happened? Okay, it's back. All right. So how did everyone do? Yeah. No. Okay. All right. Let me see. When I'm trying to share a screen, and you have a million windows open. There we go. All right. So what we've done is basically given you all of the tools you need to solve pretty much everything about the universe, as far as we know, right? And to do that, we basically just need to solve the Schrodinger equation. Depending on the system, you know how to find h, right? You know how to write h. In this case, I gave you psi. I gave you the wave function, so you didn't have to figure out what it was. And I asked you to find the energy. So we knew these parts. We just needed to find the energy by setting up an eigenvalue equation. So the first step was be to figure out what h is, right? It's the kinetic energy plus the potential energy, but I already told you that the potential energy is 0. So then the Hamiltonian is just the kinetic energy, which is negative h bar squared over 2m times the partial derivative with respect to x. Second derivative with respect to x. Remember I said we're only going, well, the wave function only has x in it. No y, no z, just one dimension, right? All right. So we can write the entire Schrodinger equation by just doing this, right? Negative h bar squared over 2m, the second differential with respect to x. The wave function was 2 over a times sine of pi x over a. A is just a constant, right? And then we know this should be equal to energy times psi. So let's first verify that this gives us an eigenvalue equation. So this is the operator, right? Let me write that in a different color. So this is the operator. Nope, too much. This is the operator, sorry. And then this part here is the wave function, right? So we're gonna operate on the wave function. Now, so the constants, right? This constant here doesn't change, right? This is the partial derivative with respect to x, but this is a constant. So like you can't find the derivative of a constant, so we can actually take that out as well. And so everything that's left is the second derivative with respect to x against this function here, right? All right. So I'm going to take, just to make this all look nice, we know that this is h psi, right? I just written it out. Okay. So the constants again stay the same. All right, h bar is a constant, m is a constant, 2 is a constant, a is a constant. Now we need a second differential of sine x. Well, let's take the first differential first. The first differential of sine x, or rather sine pi x over a, is just pi over a times cosine of pi x over a. For those of you wondering how I got that, let's let's do it. D dx of sine pi x over a, right? We use the chain rule. So we, again, once you've done this many times, you can do the this part of the chain rule in your head. But let's let some other variable, let's call it u. Let's make that pi x over a, right? So then du dx would be pi over a, right? Okay. This is a function that we want to find a differential of. Let's call it y. So really what we're trying to find is dy dx, right? But using the chain rule, dy dx can be dy du times du dx, right? So when we made the substitution of u equals pi x over a, that means our function y, which was sine of pi x over a, just becomes sine of u. All right, let me know if I'm going too fast. But then, so dy du would be, what's the differential of sine x or sine u? Cosine u, right? Um, I think all of these sort of differential rules should be in the equation sheets handout if you didn't remember it. So the differential that we're looking for, dy dx, would be dy du, which is just cosine u, times du dx, which we said here was pi over a. And again, we don't want u, so let's replace what u was. U was pi x over a. So instead of u, let's put pi x over a. So it's cosine of pi x over a times pi over a. So that's what I have. Pi over a times cosine pi x over a. Do we see how that works? Again, if you're not comfortable with these kinds of derivatives, they occur a lot. So meet with me. We can go over calculus if you want. But yeah, so that's the first differential. Let's take the second differential now. So the constants again stay the same, 2m root of 2 over a. And this is a constant now, pi over a, so I can bring it outside as well. And then now let's take another differential of this guy, right? What I end up with, if I take this differential, let me use another color so that we can see it, right? So differential of cosine pi x over a, I actually get pi over a times negative sine. So let's just move the negative sign into here, sine pi x over a. Again, I'm using the chain rule, but for with this exception, the derivative of cosine x is actually negative sine x, in case you didn't remember those. So this is what we end up with. There's a negative pi over a times sine x. So let's simplify all of this, right? Negative h bar squared over 2m, right? There's the root 2 over a. There's pi over a times another pi over a, so that becomes pi squared over a squared. There's this negative here and this negative here, so that becomes a positive, right? And then, so I accounted for that, and then we're left with sine pi x over a. Now, let's compare this to our wave function that we started with. It's square root of 2 over a times sine of pi x over a. So let's stick all of those terms together. So we have h bar over 2m. Let's stick the square root of 2 over a times the sine of pi x over a together. So then here we're left with pi squared over a squared, right? This is the wave function, right? This, there are no x's in there. H bar is a constant, pi is a constant, I said a is a constant. So this is all a constant. So this must be This is an eigenvalue equation, right? H psi is equal to a constant. We call that constant E for energy times psi. So then the energy is h bar squared pi squared over 2ma squared. You can actually simplify this further. We know that h bar is h over 2 pi. Remember that? So then h bar squared will just be h squared over 4 pi squared. So if you wanted to, this would have been an acceptable answer. But if you wanted to, you could simplify this. H bar squared would just be h squared over 4 pi squared. And then the 4 times the 2 will be 8. There's another pi squared up here, a squared, and then the pi squares will just cancel out. So the energy becomes h squared over 8a squared. All right. Does this all make sense? So to figure out whether this was an eigenfunction, we had to set up the appropriate eigenvalue equation. To do that, we needed to find right h, the operator. In this case, the potential was 0, so the operator was just the kinetic energy. Then we applied it to the wave function, right? And then from there, it was calculus. We had to do second differential of this guy. We had to keep careful track of all the units. But in the end, we got back a constant E times the wave function again. So that constant E must be the energy. And that is how we go about finding pretty much the wave function of anything. If you can write the Hamiltonian, which is just the total energy operator, for any equation, if there's a wave function that is an eigenfunction of this operator, then that wave function satisfies the system. That wave function is the wave function we're looking for. And whatever energy eigenvalue we get out is the energy of the system. And this is the heart of quantum mechanics. You solve for the wave function. Whatever wave function sets up an eigenvalue equation, that's the wave function we're looking for. Remember, we could have written any wave function. Well, not a wave function like that. That's not valid. But we could have written any wave function, but not any wave function would work for your system. Only, so maybe I should write that. Only wave functions that are eigenfunctions of the Hamiltonian operator are valid wave functions for our system. And so once you could find those valid wave functions for your system, you know everything about your system. Because remember, the first postulate when we started this whole thing is once you know this wave function, you know everything about the system. That, ladies and gentlemen, oh, shoot. I forgot one thing. Um, the M here just magically disappeared. I just realized. The M does not disappear. It's still there. Yep. There we go. Sorry about that. Lost track of the little mass there. Because this is an electron, this will be the mass of the electron, in case you're wondering. It'll be the mass of whatever particle you're looking at. In this case, it's the mass of the electron. So I just mentioned that once you have this wave function, you can get anything about, you can know everything about the system that you're interested in, right? But to do that, you have the wave function now. You need the operators to operate on it, right? And so we learned about some operators before, the position operator, right? X hat, and that's just X multiplied by whatever the wave function is, right? We learned about the momentum operator, right? and we write it as px, so the momentum in the x direction, and we said that this was minus I times h bar times d dx. There are other operators that we should be interested in. There's angular momentum operator. So all of this is basically saying if you have the wave function, you want to find a position, you use the position operator. You have the wave function and you want to find a momentum, you use the momentum operator. You have the wave function and you want to find the angular momentum, you use the angular momentum, right? Now, in classical physics, the angular momentum without the hat would be just y times the momentum in z direction minus z times the momentum in the y direction. So if we want to turn this into operators, so now instead we have the angular momentum operator, we just use the operator for y times the momentum operator in the z direction, which is negative I h bar d dz, right? Minus z operator, which is just actually z multiplied by whatever comes after it, times the momentum in the y direction, which is negative I h bar d dy. So if we want to figure out what the angular momentum in quantum mechanics, the operator is, we just simplify this, and it should simplify to, let's take negative IH bar out, so negative IH bar, and then here we'll have y times d dz minus z times d dy. That's the angular momentum operator. And theoretically, you can find all other operators from these two. Once we know what the classical operator looks like, we can use the definitions for these two operators, plug them in, and find the quantum mechanical operators. Let's look at another quantum mechanical operator. So we already know the kinetic energy one, right? It's negative h bar squared over 2m nabla squared. We Let's look at some special potential energy operator, right? So these are a couple of systems that we're going to look. Harmonic oscillator. Remember I said the potential energy depends on the system. So for a harmonic oscillator, that's kind of like a spring, right? Moving back and forth. That's the potential energy of a spring. It's half kx squared. And then another one that you might be interested in is Coulomb. I spelled Coulomb wrong.
What is K?
K is the force constant of the spring. You guys have done these before, right? Like force constants of springs. Yeah, it's half kx squared is the potential of a spring. Good question though. Yeah, I should have specified what k is. And then the other sort of potential that comes up a lot, potential, is Coulombic potential. So Coulombic potential is when you have a positive, well, two charged particles, could be positive or negative, or even positive and positive or whatever. They'll either attract or repel each other, right? And here we're not going to use x, y, and z because this potential only depends on like the distance between these two particles. We'll call that distance r. So this Coulombic potential will be a function of r. This one was a function of x. So it depends on the distance between the two particles, and that potential is Q1, which is charge on the first one, times Q2, which is the charge on the second one, divided by 4 pi E naught, right? E naught is permittivity of free space times R. And this is R, the distance between them, between charges, and these two are the charges. So we can see that if the two charges have the same sign, if they're both positive or they're both negative, the whole potential becomes positive. And positive potentials just means kind of like repulsion almost. Um, whereas negative potential means attraction. So here are a lot of operators that we'll see used in this course. Once we've solved for the wave function, we can find any of these. Any questions so far on the Schrodinger equation and the Hamiltonian?
Since some of these operators are multivariable, how would you write like how would you get like a multivariable equation that's one equation, if that makes sense?
Yeah. So that's where things got complicated, and that's why a lot of times in this course we're probably going to stick to one dimension, because
Okay.
to do the math on paper for multiple dimensions can become very, very tricky. But you can write a function in many different dimensions. For
Hmm.
example, let's, I mean, I'm trying to think of a function right now, but you can write a function that's a function of x, y, and z, right? Like x squared plus 2y plus 3xy plus 4zy. You know, that's a function of many different dimensions, right? And so you can theoretically find the partial derivative of x with respect to this function, right? df dx, which will just be, I don't know, 2x plus 3y, right? You can also find the partial derivative with respect to y. You know, you can apply operators to this function the same way you would, just that the math becomes more complex.
Okay. Thank you.
Yep, no problem. So that's the Schrodinger equation. This little thing, right? An eigenvalue equation. We know, let's put a little hat over there. Never forget the hat. It means it's an operator. That's it. That's a Schrodinger equation. But the Schrodinger equation actually only applies to this Schrodinger equation. We call it the time independent Schrodinger equation, right? And it only applies to special cases because things are not static. Things don't stay the same. Things are always moving, right? So that brings us to, and this is where I jumped forward in your textbook a little bit. If you read the sort of things I wanted you to read, let's look at the time dependent Schrodinger equation. And so here, what I want you to take away is the ability to write the time dependent Schrodinger equation for stationary states. And we'll talk about what that means in a second. All right. So there, when we wrote the Schrodinger equation, right, we said this: h psi is equal to e psi, and psi had, you know, position, was a function of position x, y, or z, depending on whether we're looking at 1, 2, or 3 dimensions. There's no time in there at all, right? Because, but as we know, things are always sort of moving. Well, most things are always sort of moving. Things are not really stationary. Um, in fact, this equation only works for what we call stationary states. And stationary states are quantum states whose observables do not change with time. Now, what does that mean? Well, let's take an atom, and there's an electron orbiting this atom. We know from like basic chemistry that those electrons orbit in orbitals, like the 1s orbital and the 2s, and we're gonna get to those later in the chapter. But the energy of the 1s orbital never changes. The energy of the 2s orbitals never changes. Basically, what I'm trying to say is an atom, electrons orbiting an atom, is a stationary state. In fact, a lot of things are stationary because their energy, their total energy remains the same. Right? So any system where the total energy remains the same, we can treat that like a stationary state. And so really that Schrodinger equation we looked at earlier can solve a lot of systems. The only time it doesn't work is when, for example, the total energy is changing. Maybe maybe something is happening to that system to change the total energy. But in a lot of cases, we know that the conservation of energy, right? Energy remains the same. And so there's a lot of systems where the total energy remains the same. So we can actually use the Schrodinger equation, the time independent Schrodinger equation. But really, and remember we talked about three postulates of quantum mechanics so far. The fourth quantum mechanical postulate, so let me write it this way. Quantum mechanical postulate number 4 is actually this, that all wave functions, and this doesn't mean for stationary states or not, they must satisfy the time dependent Schrodinger equation. And the time dependent Schrodinger equation looks like this. So it's the Hamiltonian times the wave function is equal to I times h bar times the derivative of the wave function with respect to time. So when I said earlier that the Schrodinger equation, when I wrote it like this, is the most important equation in human history, really this is actually the most important equation in human history. The time independent version was just a special case. So this little equation here has 1, 2, 3, 4, 5, 6, 7 symbols or so. That is the most important equation in human history, in my opinion. All wave functions must satisfy this equation. It's a little bit more difficult to solve because we have the Hamiltonian here, which we know how to write. But we have this extra time derivative on this other side. You notice that this is not an eigenvalue equation necessarily anymore, right? It's slightly different, but this is the time independent equation. Sorry, the time dependent Schrodinger equation. And basically for stationary states, they will obey is the wrong word, satisfy the time independent. Remember, independent means it doesn't depend on time. Independent Schrodinger equation, which is just h psi is equal to E psi, which is a much easier equation to solve. But this is the fourth quantum mechanical postulate. All equations must satisfy the time-dependent Schrodinger equation, and if you have a stationary state, which, like I said, can be a lot of cases, they satisfy the time-independent Schrodinger equation.
Do you still get an eigenvalue from the time-dependent Schrodinger equation?
Yes. Well, you solve this equation and you will always get an energy that is a real value. Whatever equations, so let me put it this way. So you had this equation, right? So when you apply this Hamiltonian to this operator, you should get back a constant times the same wave function. And that constant was the energy, right? In the time-dependent Schrodinger equation, when you do the same thing, you don't get a constant times the wave function. You get the same thing as you would have gotten if you took IH bar times the time differential of the same wave function. These two should give you the same answer.
Okay, that makes sense.
Whether or not it's the energy is a different matter, right? but whatever wave function solves this equation, that's what you get. Now we know in both cases this, in stationary states, this should be the energy times the wave function. Okay, but that brings up a good point. Remember I said all things are always moving, right? Even stationary states, while the energy doesn't change in time, the wave is still moving, right? Waves don't just stay there. There's no wave on an ocean that just stays there like a little hump, right? The waves are always moving. So even stationary states, the waves are moving. So I know that's a weird thing. So even in stationary states, the waves or the wave functions are still moving. Now, this is hard to wrap our minds around because we really don't know what the wave function means, right? Like, what does it mean for a state to be stationary, but the wave function still moves? I don't know, right? And like I said, that's probably the realm for philosophy, but that means that all wave function are functions of position and time, right? Functions of position and time, because they change from one time to the next, even though the observables don't change because they're stationary. The energy doesn't change, the other observables don't change.
Can you scroll up just a little?
Sorry?
Can you scroll up just a little?
Okay.
Thank you.
So I want you to wrap your heads around that. And that's where this third Jupyter notebook actually comes in useful. It helps you visualize how wave functions move in time. Because there's no way I can like try to draw something on this page to show you how a wave moves, right? Like, I don't know, maybe with an arrow or something. But when you explore this new Jupyter notebook, you'll see how waves evolve with time. There's some movies in there. Hopefully you guys enjoy it because it took me a long time to make them just right. No joke. It took me like 10 hours just to code one part of it. Did I have fun though? Yes. All right. So all waves are moving with time, right? There's a position and a time part. But when we did the Schrodinger equation, the time independent Schrodinger equation, there was no time, right? The reason why there was no time is because we sort of just hidden it because it wasn't important. There's no time in this equation. Really, what we should have said is the real wave function, which is a function of position and time, in these cases, so for stationary states, right? We solve this equation. Really, what we should have said is there's one part of it that depends only on position and another part that depends only on time. So here is the total wave function, right? This is the part of the wave function part that depends only on position. And this is the part that depends only on time. So when you're solving this equation up here, right, the wave functions that you sort of get out are only this part, the part that only depends on position. We don't know anything about the part that depends on time. And that's why I said all equations must satisfy the time-dependent Schrodinger equation, because we all need the time part. But the time part is actually not difficult to get for these stationary states, right? So let's examine this. Any questions on that so far? So here, what this means, it's this function multiplied by this function. There are two functions multiplied by each other, one of position, one of time. I used lowercase psi to differentiate it from uppercase psi, which is the total wave function, right? All right. So let's try to understand. Let's try to find what this time-dependent part does. Remember, this is stationary states, states that we think don't move, right? But I mentioned that all waves move. So we need to find the moving part of the wave, the function of time. So we know from the time independent Schrodinger equation, this must be satisfied, right? We know from the time dependent wave function, must be satisfied, the time derivative of the wave function. And then we know that the total wave function depends on position and then another function on time. Time function is what we want to solve for. So if this must be satisfied, right, then let's replace this with this part. Everybody with me? So we're looking at stationary states where this must be satisfied, stationary states. Again, stationary states just means states where the observables are not changing with time. There's still a time dependence, but the observables remain the same. All right. So now what we have once we've done that is the energy times the wave function is equal to this IH bar times the time derivative of the same wave function. Let's break apart the wave function. We said the wave function has two parts to it, the function on position and the function on time. So let's write the function of position times the function of time on both sides. The function of position and the function of time. This is where partial derivatives come in useful, right? We know that this function doesn't have time in it, so the partial derivative of this doesn't make, we can treat this as a constant when it comes to the partial derivative with respect to time. Does that make sense? Yep. So from this equation, since we only have the time derivative here, we can treat this part as a constant. So we can cancel it out on both sides, right? So we end up with the energy times this time function is equal to this, right? Now let's take IH bar, let's divide by IH bar on both sides. So we have E divided by IH bar times the time function is equal to the derivative of the time function. And to simplify this, it actually is negative I over E over H bar. Like these two things are the same. And I actually want to leave it like that for you to prove it to yourself. I just wanted to take the I to the numerator from the denominator. So I did that. So this times the function should be the time derivative of the same function. Now here's where I want to ask you, can you think of any function, right, where when you take the time derivative, you get this times the same function? What kind of functions where you take a derivative and you get this times the same function? Can you think of any general function that you know? Remember, I is just a number as a constant. Energy is just a number, a constant in this case, and H bar is a constant. So when you take a derivative, you get a constant times that same function.
Would it be like e to the what's out front times t?
Yeah, that function. And in case you're wondering, you take the time derivative of this function, right? You get negative IE over H bar times e to the negative IE t over H bar.
Could you zoom out some?
Sorry?
Could you zoom out some?
Oh, sorry. I realized my head is on it. There we go.
You're good. Thank you.
No, they're all there's so many awesome things that I want to like show you about these types of equations that I honestly I didn't quite understood when I was an undergrad, and some of them I didn't quite understand when I was in grad school even. But as I learned about how all like different areas of math and how they work, um, I slowly understood over the years. But this is the time part of all stationary states equation, right? So if you solve an equation, let's use the one that we used for the example earlier. We had a wave function with x like this, sine pi x over a, right? That's just the x part. And if you plot this, this is just a sine function, right? So a sine function looks like this, right? That's just a sine function. But if you, in reality, this whole function has a time part that is exactly what I just wrote, I.e. over times t over h bar. There's a time part. What does this time part do, right? Well, this time part has an I in it. And remember what I said, I means there's an axis that goes in and out of the page, like a 3D axis that I can't quite draw. And that axis um, changes with time, right? So really, even though we might draw this as a sine wave, what's happening in reality is this wave is rotating around the axis slowly, right? And and the way to realize that is, do you know this e to the I pi, sorry, is -1? Have you seen that relationship? Maybe? No? All right. I'll probably go into too much math than you probably need to know. But that's what I want to show. Even though you might write a wave function that just looks like a regular old function, the the time part means that it's always moving. And in this case, it's like just rotating around the axis. And the speed of that rotation depends on the energy. The higher the energy, the faster it rotates. The slower the energy, the slower it rotates. Right? But remember, that's the wave function. The probability, right, is related to sort of the square of the wave function. So when you do this, the negative axis goes away, right? The imaginary axis goes away because this is a complex conjugate. So you end up with a situation where you you also get positive values only, right? The negative goes away because it's squared. So this is the probability, and it doesn't depend on time because this probability remains the same. Even though this wave function is rotating, the probability remains identical. And we'll explore that in a bit too. But just to wrap up, today we talked about the Schrodinger equation, and we talked about how we set that up all the way. When did we do it? All the way up here. We set it up by using the total energy operator, which is the Hamiltonian, which we use from classical mechanics. We figured out what the kinetic energy operator is from the position and momentum operators. That's a kinetic energy operator right here. And then using that, we can write the Hamiltonian for any system once we know the potential, right? Once we have that, we can actually solve, we can write the Hamiltonian for simple systems, and we can actually solve for the eigenvalues, the energies, right? By setting up this eigenvalue equation. But then what we did learn was actually, in reality, all things are always moving and they satisfy the time-dependent Schrodinger equation, which is the holy grail of modern, well, physics, but quantum mechanics specifically. We want to solve this equation. For stationary states, states that don't change with time, the independent Schrodinger, sorry, this one is good enough. But there will always be a time part that we need to figure out. But the time part is really just this function right here. Throughout this course, I think we're only ever gonna. So well, let's briefly look at that. So when do we use the time independent Schrodinger equation? When I mentioned when properties don't change, right? And that's like orbitals and atoms, right? The orbital energies are always going to be the same unless something happens. But when we use the time dependent Schrodinger equations, it's when things like the energy when properties do change, right? And that happens because you add energy to the system unexpectedly. And one of the cases where you can add energy to a system unexpectedly is when molecules interact with some external energy source like light. So when molecules interact with light, you're adding energy to the system in the form of light, right? So the energy is changing. And so in those cases, we need to use a time-dependent Schrodinger equation. And so all types of spectroscopy, you need to solve the time-dependent Schrodinger equation. So both of these are actually very important for chemistry. If we're just looking at atoms and molecules and their properties, we use time-independent. If we want to figure out how those atoms and molecules interact with some other energy source like light in spectroscopy, we use a time-dependent Schrodinger equation. And we'll look at both in this course, starting obviously with the simpler one next class. I know I went over a bit there, but if you still have questions, let me know. Otherwise, yeah, I will see you on Thursday.